You guys, Sir DB again here uh, to discuss to you another application of the strip method on corner supported slab element. Okay, so last time I actually gave you an idea, a conceptual idea, how to approach a slab design on typical panels with holes. Okay, so this time uh, let's talk of a slab wherein the idea of putting a support at somewhere in the middle is done to ensure, or rather to ensure, maybe ensure, or to restrain the slab, the root slab system from deflecting and eventually breaking. Okay? So if I have here considerably a larger panel of slab, where the regional supports are normally at the corners here. Um, for some reasons, we need to put a support at the middle. No? So imagine I have some problems with the deflection of the slug or the equation of the slug, and I need to put the support somewhere here, okay, in the middle. So I may now divide the panel into first into a typical slab wherein the regional columns and regional beams are actually existing here. Okay, and so with this side here, basically let us assume that this slab panel is quite symmetrical, not exactly, but quite symmetrical in this form. And we are adding this support. Okay, we call this now support a corner supported element because what we're doing here is to subdivide further our slab into sub panels like this. Okay. Basically, since this part here is supported along the edges, okay, we will first take care of the weakest slab subdivisions or slab segment. In this regard, this is what you call a corner supported slab. Okay? Since these are basically supported by beams, new beams, originally by beams here on the sides, this, and this have to be designed or taken care of later. Okay? So what we need is to really concentrate on this panel. Wherein if you will notice that this part here is actually subjected into a positive bending, and maybe this one here, because of the inclusion of a support somewhere here, will be subjected to a negative bending. So in this case, your your panel will look like this. Okay, so you have here actually a typical 1/16 okay, of the original uh, slab panel, which is known as the corner supported element, slab element, and with properties given here. Okay, so I will not be discussing to you in full detail what are these properties, but it is something to do with the edges parallel to reinforcement direction. The loading is uniform throughout the area. It is supported here at one corner only. No supports are attached to those corners when we are talking about this particular slab element. No shear forces acting along the edges. Okay, no twisting moment acts along the edges too. All bending moments acting along an edge have the same sign, or it can be zero. Okay, and the bending moments along the edges are the same moments for the reinforcing bar. So these are the uh, basically the constraints we need, no, to further consider this application or this procedure as a part of our maybe investigation or replicating analysis. Okay, so basically this is what the slab will look like. We're referring here at these edges. Uh, these are what? These are actually support edges. Okay, uh, these are negative moment edges, and these are mid edges or mid span uh, sides or edges. That's why it is as a subscript of F here. So these are positive moment edges. And notice the distribution of moment is quite assumed, no? To be a stepwise distribution. Okay, so the side here, since it is nearer to this column support, will actually gain a positive moment which is greater than this which is further from support. Okay. Also, so is true with the support edges, negative moment edges, wherein this is bigger in terms of a stepwise unit distribution than somewhere here at the remote, okay, location far from this column support. Okay, and basically this is not, these are not of equal length, so rectangular like that, we have here A and B. So the distribution now will take to be considered at the distance, one half of the distance of the edges, the panel edges of your slab. And if we gonna take a look at the free body diagram of this in terms of section, uh, this is just like a cantilever beam with, of course, some restraining moments coming from the slab itself. The slab here will restrain it from dropping, although it is not. There is no support here, but because of the continuity of the slab here in these two directions, you have some restraint coming from uh, this one. Okay, so this is an average moment at the transverse span of equivalent to B dimension. We take the average of this. So this is the mean, the mean or the average. Of course, your reaction here will simply be equal to W times A, okay, multiplied by B here. Okay, so this WB times C. Okay, furthermore, if we are going to look at a simpler assumption for the purpose of computation, is we can actually assume a distribution here in the positive, sorry, in the positive mid-span directions along both axes or both directions to be an average, okay, a mean, an average of the positive moment here F1 and F2. Likewise here at the y direction, F1 and F2. Okay, but in this case, we're in the support will allow more energy to be absorbed that we got, then we can come up with, instead of averaging, we can come up with uh, concentrating your your moment at the mid-half meter the support here by multiplying the average negative moment here by 2. Okay, so there's a twice distribution, and we assume the further location, okay, along the support edge, the column support edge to be 0. Okay, this is the recommended distribution by Hilderberg when it comes to the strip method. Okay, alternate recommendations may be done, okay, using a zero point 0.5 and 1.5 in terms of MXS1 and MX2 as well as MYS2 and MYS2. So the following restrictions must be accounted for in the design. We have to check on the difference between your positive and negative moments to be uh, within the range. Sorry, to be at least no to be exactly equal to alpha WA squared over 2, where alpha will give you a range value from 0.70 to 0.25 or 0.25 rather points. So this will also be ranging from uh, less than or equal, greater than equal to 0.70 WA squared to and 0.25 degrees. So for an example, just to give you how this will be done using uh, a procedure on this, if I have here a this is 1, 2, 3, 4, 4 over 16 is up to 1 4. This is 1/4 of your actual slab panel. Your actual slab panel. And basically, what we did is we tried to make use of a sub panel here, divided again by 4, but this time on the basis of noting that since this is a simply supported edge, then we come up with a prop cantilever again. Okay, wherein this is a 5/8 3/8 subdivision Schwarzschild positive moment, okay, mid-span moment is located, and this is WL squared over 16 and WL squared of 8. These are actually based on elastic. So the pop problem does not conform to the restriction recommended by Hillerberg for alpha, okay? Which is in between 0.25 and 0.7. So that's it for the procedure, no, on how to deal with a scenario wherein you have a larger, considerably large panel that you want to retrofit maybe to re-strengthen by placing a support at the center, somewhere at the center, and then considering the weakest portion to be designed in terms of a corner support and stuff. So I hope you have gained some idea on how to apply this in actual problems. So thank you for listening, and I'll see you on the next video.